got the slides here. There we go. All right. There are three basic things you do in cryptography. Well, maybe four. There's hash functions, symmetric encryption, asymmetric encryption, and then signatures. Those are probably the four major functions. And hash functions are a big part of it. So that's what we're talking about now, and we'll talk about the different types of hash functions there are. Now, the idea of a hash function is to make a sort of fixed size, relatively small number that represents a file or a message. You take a bigger object typically, and you make a small sort of thumbprint to put on it, which is the property you want is that it verifies that this object has not changed. Any change in the original file will change the hash, and you shouldn't be able to find another file with the same hash. These are desirable properties. And so use them for digital signatures. It's used in public key encryption to authenticate messages and verify the integrity of files you might download. And it's used to store passwords. Instead of storing passwords in plain text where they can be stolen, you hash them. And then if somebody steals it, it's not easy to reverse the hash back to the real password. So that's how you make a fixed length fingerprint. You feed in a message of any length, go through the hash function, and you get a fixed length hash here, which serves as like a fingerprint. It is not encryption. There is no key, and there's no way to reverse the hash back to the message. There is a process called hash cracking that we'll talk about, where you can sometimes retrieve things from a hash, but it's not perfect, and it often fails. So there's non-cryptographic hash functions, which are around because there's another use of hash functions not involved in cryptography, which is just in computer science. If you're trying to store a lot of data in computer science, and you want to store it in a table, it often turns out to be a good idea to have an index to store it, and that index is calculated from the input to make like a simple address to store it in the table. And you try to make it so the address is sort of randomly related to the input data. So you might do something like add up the ASCII values of all the characters and then make it modulus something like 1,000. And that would just give you a number that was essentially random from 1 to 1,000, and that would tell you which slot to put it in the table. And this turns out to be an efficient way to store data, an efficient way to retrieve data. Those are hash functions used just to create a sort of index label to find data, but they're not intended to be cryptographic, they're not unique, they're not hard to predict or hard to fake. They serve a different purpose. Another one is cyclic redundancy check. This is I think a 32-bit hash created. And now the original hash function, by the way, you could say this, was parity. ASCII only uses 7 bits out of a byte. And their bytes have always been 8 bits, so they made the 8th bit used for parity. So you have either even parity or odd parity. And if you had even parity, then the number of ones in the byte was always even. If you had odd parity, the number of ones in the byte was always odd. And that way, the idea was, on old networks, there were a lot of errors. So if you had a byte transmitted, and one of the bits flipped during transmission due to noise, you would detect that because it would break the parity. That's an error correction mechanism. And that's fine, but then what if 2 bits flip? You won't detect that, so it's not perfect. That does detect the most common error. Now, but another thing you can have, in Ethernet has a better thing, is cyclic redundancy check, which is a 32-bit integrity check. And so when you transmit an Ethernet frame, you transmit the data and the addresses and everything, and it includes a CRC. You calculate the CRC and make sure it matches, and then you know that frame has been correctly transmitted. If it fails the CRC check, it's discarded and retransmitted. All right. So now secure hash functions are ones that have the cryptographic properties we need more than those other ones, which provide protection from, say, random noise errors, but they do not provide protection from malicious hackers. You could easily manipulate a frame, change it, and make it so the CRC still comes out the same. That's not hard to do. So this was never intended to stop a malicious attacker. It just intended to detect normal transmission line errors. All right, so digital signature is one of the most common uses for hashing. So you have a message, then you hash it, now it's smaller, then you sign that. This is a common thing you do, just so the signature doesn't have to be designed to handle a large input. But the hash function must be secure. You're trusting that the hash is uniquely tied to the message, that there isn't some way to alter the message and still have the same hash. So another thing you want is unpredictability. We talked about this before, confusion and diffusion. So if you go from a lowercase a to a lowercase b, that's only changing 1 bit in the ASCII representation, and here's maybe changing 1 or 2 more bits. And you do that, SHA-256 changes all over the place. The whole thing changes a lot, even if you change 1 bit of the input. This is what you want. There's no pattern. It's not like the small values of input have small values of output or anything like that. Any change in the input creates random, widespread changes in the output. That's what you want. So you can look at a list of these and you get no information about what was hashed to create them. All right, now the problem with hash functions is, in principle, none of them are really unique because the message can be long. So suppose the message is 1024 bits long and the hash is 256 bits long. Well, then there's 2 to the 1024 messages and 2 to the 256 hashes. So clearly, there are not enough hashes to have a separate hash for every possible message, not even close. There are many messages that hash to the same hash value, in principle. But what you want is one. Now, this helps explain one-wayness. You can't reverse hash, as we can say, because since there are many different messages that hash to the same value, knowing the hash doesn't tell you which one of those messages it is. So you can't reverse it. It's not encryption where you can decrypt. It's hashing, which creates a fingerprint number you add to a file, but it doesn't, and that number can be used to detect if the file has been changed, but it doesn't, there's no easy way to go from there back to the file. All right, so one-wayness is true of all these hash functions in principle. You can't reverse them. However, the more careful statement is to determine how much pre-image resistance you have. So pre-images work like this. If I give you a hash value, can you find any message that hashes to that value? Now, in principle, there are many messages that hash that value. So the question is, how hard is it to find a message? And that's called the pre-image resistance. If all I do is give you a hash value, like say all zeros or something, can you find a message? How many guesses will it take for you to find a message that has that hash? That's a measure of your pre-image resistance. And so if I have a hash of n bits, then if I start guessing inputs, seeing if the hash is all zeros or whatever value I'm looking for, I'm just going to have to try 2 to the n guesses, right? Each guess has a random chance of hitting something, or 2 to the n possibilities. I'll have to guess approximately 2 to the n times. So for a 256-bit hash, that's 2 to the 256. Remember, we talked about this. Even 2 to the 100 is an impossible number of calculations that all the computers in the world, given all the time in the world, can't do. 2 to the 256 is undoable. So it has strong pre-image resistance if there's nothing wrong with the mathematics of your hash function. And then there's second pre-image. So if you have a message and its hash value, can you find another message that hashes to the same value? That's the second pre-image, and it's essentially the same as the first pre-image, right? It's the same work as finding one. However, there are certain situations in which you can carefully construct 2 messages with the same hash, even though you cannot solve this problem. You can't start from a hash and find the message, but you can carefully construct 2 messages that are related and will end up with the same hash. And that's what we're going to see later with length extension attacks. All right, so every hash function in principle has collisions. A collision is if 2 different messages hash to the same value. And in principle, every hash function has to have them. In practice, though, what you try to, and that's because they call it the pigeonhole principle. If you have 10 holes and 11 pigeons, then at least one hole contains more than one pigeon. And we have, an infinite number of messages and only a finite number of hash values. So, but if we're going to collision resistance means even though the collisions exist, they are so rare that you can't ever find one. So that's the point. You want it to be practically impossible to find one in any reasonable amount of time. So, and that's when you talk about the birthday attack. If you wanted to find a collision, you could just hash random values and write down all the hashes and how long before you'll find one. It turns out you don't have to do 2 to the n calculations to find a hash of n bits that collides. You need to do the square root of that, 2 to the n over 2, because once you've done 2 to the n over 2, there are about 2 to the n pairs. The first one might match the second one, the first one might match the third one, the first one might match the fourth one, and so on. So the number of pairs is approximately the square of the number of images you've calculated. So you only have to calculate up to the square root of the number of hashes. So if you have a 256-bit hash, you only need to calculate 2 to the 128 guesses to getting there, which is impossible. But it's 2 to the n over 2 hashes to find a collision. All right, that's the game. That requires 2 to the n over 2 calculations and 2 to the n over 2 units of storage, because you're going to have to store them all to find out there's a collision in there. So, that might be possible for short hashes like MD5, but it's not possible for things like SHA-256. So if you look at MD5, it's 128 bits long. So if you wanted to do a pre-image attack, where I just give you a hash value and you have to find an input that'll make that hash, it's going to take something like 2 to the 128 calculations to do it. You don't need to store them, but you just need to compare each one to the target. So you say, how hard would it be to do 2 to the 128 calculations? And here's the answer. People have tried to test this. The 56-bit cipher, DES, was cracked in the late 90s by a brute force attack. So they were able to do 2 to the 56 calculations with a network of about 10,000 servers in the 90s. And RSA Security made a bunch of challenges. So a 64-bit key was cracked in 5 years, with 5 years of computing in 2002. And a 72-bit key attack is in progress, and they've gotten 6% to the key space as of a couple of years ago, and they say it'll take 127 years to test all the keys, which might make it sound stupid. But remember, computers don't stay fixed in power. They keep getting faster and faster. So 127 years at the rate of a few years ago might not take that long. But anyway, a 72-bit brute force attack has never been accomplished. Okay, so that gives you a clue that 128 is pretty bad. Now, another thing you can think about is if you take Bitcoin, Bitcoin is probably the best measure of practical computing power. People make a lot of money by calculating hashes, and they say the total hash rate of Bitcoin has now reached about 2 to the 93. So, in principle, if you could motivate all the people in the world to build the fastest computers in the world and use up the most power, in a year, they could probably crack a 93-bit key by brute force on the Bitcoin blockchain. So that's pretty much a measure of the maximum amount of calculation you could do on the whole planet. You might be able to crack a 93-bit key in a year. So that's a measure. And so if you consider the maximum computing power available to anyone is, say, 2 to the 96, just to round it off, then the pre-image attack takes 2 to the 128 calculations, so your safety margin is about 2 to the 30. Really 2 to the 32 if you want to look at it, but that means 2 to the 30, and 2 to the 30 is a billion. So that's a pretty good safety margin. All the computers in the world could crack it in a year, but if it's a 128-bit key, it would take you a billion years to crack them, which is probably safe enough to be, that's something you could call impossible. So the naive birthday attack, now if you take 2 to the 64 inputs, and then you calculate those hashes, and you store them using 2 to the 64 units of storage, is that possible? And it is possible. I mean, 2 to the 64 calculation is not impossible. 2 to the 64 bytes of storage is 16 million terabytes, and the entire world's storage, that's 16 exabytes, and the entire world's storage is 2,500 exabytes. So if you got a large portion of the entire resources of the planet to do it, you could probably do a naive birthday attack and find a collision in MD5 this way. You'd have to, no reasonable attacker can do it, like a reasonable crime gang or something, but a really powerful nation state like, say, the United States NSA, if they really wanted to do it, they could probably do it. It would be huge, like a moonshot, but in principle it could be done. So here's a measurement of the worldwide storage capacity to find out if that's possible. So in principle, it could be done. If your attacker is so motivated that they're willing to invest that kind of resources, then that could be done. But that would just find a collision. Now, the pre-image attack is the same thing we said before. If you have input, if you have a message and a hash value, and you're trying to fit that particular hash value, that's a second pre-image, or you're trying to do a first image, that's totally out of reach. Even all the computers in the world running for all the time you could possibly use would never get there. So that's the thing to know, even for MD5. All right, so if you want to look for collision search, we've done this project already. This is the method that seems to work best, rather than just using sequential methods, is start with a seed, hash it, then hash the hash, and so on. And what happens is, eventually, sometime you will hash a hash and it will repeat one of the earlier hashes, and from then on you'll just go around this loop. And it turns out that it's about if n is the possible total number of hash values, the tail length is about the square root of n, and the circle length is about the square root of n. So if you have a 32-bit hash like CRC32, then it's going to be 2 to the 16 calculations until you enter the loop, and 2 to the 16 around the loop, something of that order. And 2 to the 16 is 65,000. So it'd be about 65,000 on something of that order to go here, and 65,000 around here. If you had a MD5 hash, 128 bits, this would be 2 to the 64 calculations, and this would be 2 to the 64 calculations. So that's not impossible, but it would take much more than an average laptop running for a normal amount of time. All right, and so that's one way to find a hash collision. So there are ways to do it. Now, one way you can do it, the simple attack, you'd think you have to remember all the hashes and you have to do all the calculations. But what you can do is you can save just distinguished points. This is the way you do this without using a ridiculous amount of memory. You store only hashes starting with many zeros, like the first, you figure out how many zeros are likely to happen, but you only remember some of them. Because remember, you don't need to remember every one. Suppose you only remembered every 10th one. Then you'd remember H10, and 11, 12, 13, you go around a few times, and remember your H20, you'd still eventually hit the H10 again. Next time around, you'll notice, wait, I'm matching it. So it would cost you perhaps a few more calculations, some portion of the going around the circle a little further, but you wouldn't have to have much memory. You'd only store much less memory. So that's the technique, storing distinguished points. It's a time-memory trade-off. You can use a little more time to use a lot less memory. And this is often the case. You can trade time for memory. So here's distinguished points leading to a collision. Another diagram showing it. And we did this in the project last time. You can do, for really short hash functions, you can just do it easily in Python. So let's try a Kahoot. This is 141, and we're chapter 5, I think. Chapter 6, all right. Now I can sort these things. Used to be able to sort these things. They've changed the look of it, but yes, it's sorted. Good, 6A, here we are. I gotta move this side in a bit. Good. Oh, that person put the number in both places, which was not bad. Anyway, maybe they're coming back. Ah, good. Okay. I'll give it a little more time, see if we can get more than 3. All right. All right, so which hash functions have collisions? Yep, all of them do. Every hash function has collisions because there's a huge number of possible inputs and a small number of possible outputs. All right. The only issue is that for more secure hash functions, you can't find the collisions. All right, how many calculations will it take to find a message that hashes to a specific 32-bit hash, like all zeros? Yep, 2 to 32. You'll have to try approximately that many guesses to hit any particular hash value. Very good. and that's what it would be for CRC, and that's not a very big number. 2 to the 32 is a number you could reasonably do on any computer. All right, how many calculations will it take to find a hash collision for a 32-bit hash? You don't care what the number is. Yep, 2 to the 16. If you calculate 2 to the 16 numbers and you store them in a table around that time, you'll probably find that there's a match in that table. All right, the square root. All right, so which method uses more RAM but fewer CPU cycles? This is what rainbow tables do. What rainbow tables do is pre-calculate some of the calculation and put them in memory so you can just look them up instead of calculating them. So it makes your CPU processing faster, but uses up more RAM. All right, what method uses more CPU but less memory? That's the row method we talked about, where you only store some of the hashes you find instead of storing them all, and the penalty is it will take you a little bit longer to find the fact that you're stuck in a loop. All right. All right, what method uses more RAM and more CPU? That's blockchain. We haven't talked about it much in this course, but blockchain is incredibly inefficient. In blockchain, like Bitcoin, every single miner mining Bitcoin has to have the entire blockchain, all the data. They have to store all the data, and they have to do tons of calculations over and over again. So a job that would take a certain amount of RAM and CPU to put on one machine, like a normal database, you end up making like 1 million copies of the database and reproducing tons of unnecessary calculations. It uses a lot more RAM and a lot more CPU, and the benefit is you achieve this strange situation where nobody can control it. No government can shut it down. So that's why blockchain hasn't really gotten too popular. The only point of blockchain is to escape government control. And to do that, you pay a very high price using a lot more CPU and a lot more memory. And there are some people that want to make that trade, but not that many, so it hasn't become that popular. All right. Go back to the slides. All right, so now we're going to build a hash function. All right, so one way you typically do it is you break your message into blocks, just like you do for encryption, and then you process each block using compression or permutation. So this is the compression-based function. This is what MD4, MD5, SHA-1, and SHA-2 all use. So you have an initial value, IV, a random value put in here, and then you feed in a block of message, and you compress them to create an output which you use as the input for the next block and compress and so on. And the final block is the output. So it's sort of like AES CBC, cyclic blockchain, CBC mode, where you take the output of one block as the input as the IV for the next block. This is a way to do it. You got to pad the last block to fill it. So the way they typically do it is pad with 1, then zeros, and finally the message length. So if you have an 8-bit message like this, then you'll have the message, and then a 1, then a whole bunch of zeros, and then at the end you'll have 8 in binary, which is this. That's how you'll do it. Some way to fill up the last block. So the compression function often just uses a block cipher. You've got ciphers, they'll work. Use the message block as a key and encrypt the input with the key, and then you XOR the input and the output together. The XOR feedback helps make it more difficult to decrypt. So that's one way to do it. There's other ways to do it too. I was looking to see who's coming in. Anyway, There's other compression functions out there that have various limitations. They're more complex than using an encryption function, or they require the message block to be the same length as the chaining value, which is fine. It doesn't really matter which one to use. But that's the old-fashioned technique used by most hash functions that we're using. Now, there's a new technique using a sponge function with no key, and this is keycheck, which is used as for SHA-3. And so what it does is you have the first block of message, you XOR it with an initial value. You have an internal state that starts with something like all zeros. Then you XOR it in, and you have a permutation that transforms the internal state to another value of the state of the same size. So you feed in the message XORed with it, and you have part of this that's not XORed with it because the hash internal state is probably longer than your message. And then you permute it and just keep doing that over and over. So you just add the message in and keep permuting it. And that's called the absorbing phase, where you absorb all the message values. And then you have this big internal state. And then you have a squeezing phase, where you squeeze a little hash value out of that big internal state. That's the idea. And that's what SHA-3 uses. So MD5, here's the SHA family. This was broken in 2005 to generate collisions. Now, you still can't do a pre-image where I tell you I give it the hash and you have to find an input that'll make the hash. That problem would take 2 to the 128 calculations, and that has not been done. But what you can do is you can carefully construct two messages that are related that create the same hash value. And that's the issue. So SHA-0, the original SHA, was approved by NIST in 1993, but the NSA told people, for secret reasons we won't tell you, you should change it. Because they had a technique that would crack it that was classified secret at that time called differential cryptanalysis, and they used it to warn the external world to use a better hash function, which is a case of the NSA actually improving public cryptography with their secret information instead of the unfortunately more common situation where the NSA poisons public cryptography so they can get in. So that's what they did. The original NIST was 160 bits long, so it should have been effectively uncrackable, 2 to the 80 calculations to find a collision, but they found an attack that only took 2 to the 60. And later attacks can do it in as little as 2 to the 33 to find a collision. So turns out it's not that good. This was for SHA-0. So SHA-1 uses an encryption function called SHA-cal and repeats this calculation. It encrypts the message and the hash, and then adds the hash, and then that calculates the next layer of hash there. For every block, it takes the encryption of the message and hash and combines it with the hash with, I think this means XOR, and then makes it here. So it's sort of like that row method where you keep hashing the previous hash value. And it's got a compression function. So what it does is it breaks your 160-bit state into 532-bit words, and this is the compression function. You run a block cipher on them and combine them. And so, anyway, there are a bunch of attacks. In 2005, they found an attack that would find a collision in 2 to the 63 calculations, and Google published this page called Chattered. They made 2 PDF files that looked different but cached to the same SHA-1. So that's a collision that's been found. And so people don't want to use it anymore after you found a collision. That's considered a weakness. If you understand this in more detail, you'll see most of the case you care about is the first pre-image resistance, and that remains essentially impossible, even for MD5. But anyway, there are collisions in SHA-1, and that makes people not like it. So they don't trust it, and they want to move to something else. So SHA-2 came out specifically to be the upgrade to get away from SHA-1. It came in various sizes, the most common being 256. And this uses 8 32-bit words and 64 rounds of calculation with a more complicated expand function, but the same general structure as SHA-1. So SHA-2, as far as anybody knows, it's very strong. There's no significant flaw in it, but people got concerned because the algorithm is close to SHA-1, and SHA-1 turned out to have some serious shortcuts you could do, as we saw. So people worried that even though SHA-2 has not yet been broken, it might be broken. So they wanted to break SHA-3 so we have it when SHA-1, in case SHA-2 fails. And so they had a contest for about 5 years where the National Institute of Standards would get competing algorithms. And here's some of the ones that competed. And the one that won was keycheck. So completely different, uses a sponge function. The internal state is 1600 bits. And as you saw, you insert the message in the absorbing phase, and then you squeeze out just some of the bits to make the output. So you have 1600 bits internally, but then you can squeeze out different lengths at the end. So you can make a 224-bit hash or a 512-bit hash or these others, and you can in principle make hashes of any length. There are two extendable output functions called shake128 and shake256. They can produce a hash of any length coming out of it. So that's what the SHA-3 approval is. Now, there's another one called Blake 2, a newer one, and this is a pattern in this course. The ones you've heard of, the ones that are famous and approved by the government, are old, like a decade old or more, mostly, and there are new ones that have been developed by mathematicians that are in principle better, but they're not being used by anybody much yet because the old ones are the standard and they're good enough. But they made better ones, like Blake 2 is as secure as SHA-3 but faster to compute, faster than any of them. It's got two functions. Blake 2 is designed for 64-bit calculations, and Blake 2 is designed for 8 to 32-bit calculations. So, I'll turn this on so in case. All right, so here's how fast they are. Here's the speed, and you see SHA-3 512 is really slow. The other SHA-3 is still pretty slow. SHA is faster. MD5 is even faster. SHA-1 is faster, but Blake 2 is even faster than SHA-1. So, you know, that's why it's a superior function. It's as secure as SHA-3, but as fast as SHA-1. So if there was no other issues to consider, we should all be using Blake 2B, but we aren't because the other one was, approved by the government and became a standard. And nobody moves off a standard just because there's something that's a little bit better. You only move off a standard if there's something really wrong with the standard or there's something new that really is a whole lot cheaper. All right, so it's the fastest secure hash available today, and it is being added to some modern libraries like Shodium. All right, so it's got a counter and a flag. It's got a block cipher based on cha-cha, which is based on salsa, which we talked about last time. So you take the two halves of the state, which are XORed together after the block cipher, right? So you feed in your parameters, your block of message goes in here, used as the key to encrypt this internal state, and then you XOR these things together at the end and repeat this. That's a round of it. And here's the core operation. You have 4 64-bit words, and here's the transformations. And as you can see, like the other things we've studied, these are simple things like XOR and shift to the right, shift to the left, addition, simple operations designed to be fast on computers. All right. So what can go wrong with hash functions? The simple thing is you use a wrong hash function. This is the number one problem. I was just talking about on Pulse Security Weekly. The most common problem with cryptography is people use it incorrectly. They use the wrong cryptographic system for the wrong way. So you use a weak algorithm like CRC32 for file integrity. That's not going to work. That system is not strong enough. It's not a strong enough hash. It's easy enough to forge a message which will have a CRC32 you choose. Then there's the length extension attack, which is how the hash collisions are found in MD5 and SHA-1. If you know the hash of a message, you can add more data to the right. Remember, it goes by putting in a block of message and another block of message and another block of message. So if you put in a message that only fills 2 blocks and get the hash function, you can add more to the end of it. So I can take 2, and so I can add more and calculate the hash. If all I know is the hash of this message, but I don't know the original message, I can still figure out, I do not know M1 and M2, but I know this hash value. I can just perform the operation to add more data to the end and predict that from this hash value. I can transform the hash value of a shorter message into the hash value of a longer message with data added to the end because of the way this thing is constructed. That's called a length extension attack. So here's the analytically, I can use the hash of message 1 followed by message 2 to generate the hash of message 1, message 2, message 3. I do not need to know message 1 or message 2. I can just add message 3 by doing another round of the hash function on it. And so this can fool some applications, just like we were talking last time about the attack against AES CBC, how sometimes this will get you in a system because the fact that you can create a message which can be decoded and has some meaningful data in it might convince the system that you are authorized. And here, my ability to create a valid hash value of a longer message might fool some systems into thinking I know the secret. So SHA-2 is also vulnerable to length extension. They all are. In principle, this could have been avoided if you just made the last stage different than the previous stages, then length extension would not work. But nobody thought of that when they designed MD5, SHA-1, or SHA-2. They're all vulnerable to length extension because they just keep repeating the same algorithm at every step. And that's what Blake does. Blake just uses something different at the end, so the length extension is not a problem. And so, here's an example of what you might do. A cloud server verifies, like think of Dropbox. I store files on Dropbox. It verifies that it stored a message M. So the client picks a random value C as a challenge. The server computes the hash of M followed by C as a response. The client also computes hash of M followed by C and makes sure that it matches. And so, as you can see, a server could cheat by only keeping the hash value from hashing the message and discarding the message. They could still calculate the response by link extension. So that's the problem. You can pass certain tests here without actually knowing the message because you know the hash of the message. So you can't reverse the hash and find the message, but you can predict the hash of a longer message that begins with the same start. And that's very much like cipher block chaining. That is a failure of your cryptographic system, so you can forge something you shouldn't be able to forge. It's not completely broken, but you can do anything arbitrary, like find a message that will create a specific hash, but you can do some things that you really shouldn't be able to do. So, let's try another Kahoot. All right. All right, so which hash uses a sponge function? SHA-3, that's the newest one, okay? Which one uses a Merkle-Damgard construction? All of them do. They're all based on this, where you just do a series of iterations all the same, which is what they wanted to get away from. Moved to SHA-3, so it wouldn't have the weaknesses that all these share. All right, which one uses Keychak's method? I'm probably pronouncing that name wrong too. I have no idea what nation he's from or what language that's. SHA-3 is Keychak, yeah. All right, which hash collision was found in 2017? Yep, SHA-1. And which is the fastest? Yep, Blake is the new one, faster and more secure. Stop this recording.